Okay, good. Thank you for the introduction, Eric. Yeah, I'm going to talk today about high-strength aluminum alloys processed by laser additive manufacturing. I just wanted to add some more names in the list of co-authors. I'm not alone in my group working on this topic. Riccardo Casati is a colleague of mine working in our material group of Department of Mechanical Engineering. Filippo Bellelli is doing the PhD on this topic exactly. Zara also worked on aluminum alloys and is still active in this topic with us. Milad was a former PhD student at Polimi, now was working in a Roland group. And there might be many other master students. So today, the outline of my talk will be on the processing of high-strength aluminum alloys. I will be talking about a strategy to control solidification and to avoid some troubles that may arise during the solidification of these alloys. And then I will shift to discussion on the opportunities for thermal treatments, targeting the strength improvement and the relaxation of residual stresses. This is a very introductory slide. Don't worry. I know that we all know about what we're talking about. It's just a few pictures about a well-processable aluminum 10 silicon alloy, very popular, nothing special. Just to tell you that when you look at the microstructure on left-hand side, by the way, I can use the pointer. Okay, on left-hand side, this side here, we have the view about the different laser track seen from top, let's say on a plane which is normal to the building direction. If we do a lateral cross-section, we see very distinctively the melt pools, and we notice the columnar grains that are growing according to the thermal gradient. And if we increase even more the magnification, we can see a very nice cellular structure, very fine, which can be found inside those columnar grain. Well, for this kind of alloys, everything goes very smoothly during processing. Usually, you don't have any specific trouble with defects, provided the parameters are set according to the best option. If we move to high-strength alloy, then lots of trouble come around. And you can see here, this is, for instance, 2024 aluminum alloys, aluminum, copper, magnesium alloy, but the same holds for 7000 series alloys and for some 6000 series alloys. You can see again the same kind of band pools, but this time very often you can see cracks that are running usually intergranularly along the columnar grain, right? So it's really a disaster when you go for additive manufacturing lasers, at least additive manufacturing of very high strength aluminum alloy. So there is a kind of, originally there was a kind of gap in the palette of the material available for the manufacturing of demanding parts for the aerospace, for the motorsport, for many applications. And this kind of concern is nothing new, actually. I brought out from my very old files some micrographs about the welding microstructure, the microstructure generated during welding of 7050 alloys. It's about lots of years ago, but the problem was always the same. Again, here we got hot cracks at the grain boundary of the heat effective zone, but also in the weld metal zone. So nothing new. But of course, we have to consider laser additive manufacturing as a kind of mini welding operation, which is repeated lots of times to produce a kind of 3D part. So we can rely on the experience, on the expertise we have on welding. It's about hot cracking in aluminum alloys. There are so many factors of influence. I put here a list, but before reading this list, we can maybe comment a very simplified scheme about what happens during solidification and what kind of concerns we may have. So this is let's say a standard process of solidification according to which dendrites, or let's say columnar grains, are growing from left to right. The thermal gradient is according so that hot part is on the right of the boxes here, while the chill zone is on the left. And the dendrites are growing rightwards. And in the very last stage of solidification, we all know that we may have large fraction of solids. Still, we can have some films or some pocket of liquid, the yellow zones. And when shrinkage stresses are set up, because we may have some bridges that are connecting laterally the dendrites, we may induce solidification cracks, or hot shears. There are several names for the same phenomenon, basically. What can we do against that? Well, there are many strategies. Let us talk about a couple of them. One of them could be to decrease the so-called freezing range, so the interval of the solidification, the temperature interval of solidification, so that there will be a much shorter interval in terms of length, in terms of time, in terms of temperature gap, along which the critical condition is set, so that crack, they have much lower chance to grow. Another strategy which could be very effective is to switch from columnar grains to equiaxial grain. By this method, we're going to have lots of much more interface where the solute, where the liquid pockets can spread around. The stress can be distributed in a different way, so that we end up having much lower and or sometimes no cracks anymore. Among the main factors, of course, there is a freezing range. We mentioned it. The amount of the extent of the shrinkage stresses, the grain morphology, equiaxial versus columnar, and many other. More in detail, crystal misorientation also plays a role. The larger the crystal misorientation, the higher the probability of having cracks. Segregation at the boundaries, of course. The liquid pockets are also stimulated by low melting point constituents. Of course, the environments around this liquid, the thermal gradient, the growth rate, and everything that goes with them. The liquid properties in terms of capillarity, surface tension, and many other things. So it's a very complex scenario. In the following of my presentation, I will try to give you some suggestions, some hundred suggestions about what we can do for the design of high-strength aluminum alloys, trying to avoid this kind of constant problem we have to face. So first one was to manipulate somehow the freezing range of alloys. Indeed, looking at the plot here on the left-hand side, we realize very easily that those alloys that have a very flat, let's say, solidification curve in the very last stage of the process. This is a plot showing temperature against the fraction of solid. So fully solid is here, and solidification is 1, okay? Very starting of the solidification right here, temperature decreases. Okay, you can understand that for a well-processable alloy, aluminum silicon 10, the blue line, there is a flat portion of the curve in the very end portion, stage of solidification, while non-processable alloy, such as the 7075 alloy, usually has a very sharp drop in temperature in the last stage of solidification. So higher stresses, higher chance to get cracks. What can we do in order to smooth down, to make flat, to produce a flat curve in the last stage of solidification? Okay, we can play with the chemistry, of course, for instance, inducing a large amount of eudectic constituent in the alloys. We can modify somehow the composition. You can see it from the plot here on the right, which is a very old plot. Actually, I couldn't track back the reference, so I'm sorry for the authors that are not mentioned for this plot. But it shows that it comes from welding again. It shows that when we go with for aluminum and silicon alloys, usually pure aluminum can be processed quite easily, no cracks. There is a critical range of silicon that produces crack, but if we increase the amount of silicon, such as in this 7%, 10%, 12% silicon alloys, there are no cracks anymore. We induce lots of eutectic constituents. The same was also for copper, which is a dramatically dangerous element for the cracking. Indeed, 2,006 alloys, 7,000 alloys, those that are critical, they contain lots of copper. And again, you see here that we go through a critical range, but again, if we increase the amount of copper, then we can decrease the cracking sensitivity. Okay, we will talk about that later. If we move on the plot in the middle of this slide, we have a good example, I guess, at least. Okay, again, there is a comparison among similar alloys as those we got on the left side. The red line, these are DSC scans, so differential scanning calorimetry runs, tests. The red line shows the solidification curve for quite similar alloy. It was a 70, I can't remember, anyway, 7,000 series alloy. It shows that there is a very wide peak corresponding to the solidification and a small tail right here, okay? More or less, all the solidification process develops over a quite large temperature interval, more or less the same information we got from this diagram here. While the blue line, the black line is for an aluminum 7% silicon. Not exactly, but pretty much the same behavior as the blue line here. So we have primary solidification of alpha aluminum, and then in the end of solidification, another bump, another peak, very large, very wide as well, that corresponds to the eutectic aluminum silicon solidification. Okay, this is a good point because the large amount of liquid which is available in the very last stage of solidification can smooth down the curve, can possibly also promote healing, backfilling of the cracks and healing them. Okay, but you end up having a very sound microstructure. What can we do? Let us try to mix them. To mix these two compositions. It was a very, let's say, preliminary job. Some years ago, we did that. We tried to mix those two powders, and we processed them by laser powder bed fusion according to proper, let's say, fraction. And the resulting curve, I was wrong. Okay, sorry, the black line, okay, is for the aluminum, and again, aluminum silicon. We have primary aluminum and lots of eutectic. Okay, sorry. And by mixing the red and the black one, we got the modified alloy, which again shows a peak for the primary aluminum, and then in the end, another peak for the eutectic. Okay, this happened in a 7,000 series alloy, which was modified with an excess of silicon. And again, as I told you before, I was wrong in showing the alloy, but the concept is always there. We have backfilling of the crack, we have excess of silicon of eutectic in the end solidification that helps in removing all the cracks or help in avoiding formation of cracks. We got a very sound microstructure in the end of solidification. Okay, this is another example. I was talking about the effect of adding more copper than the standard composition. It's an experimental work we did on 2024 alloy, the one that showed lots of crack in the beginning. If we process non-standard aluminum 2024 alloy, so 4 copper and something like 1.5% magnesium, at the end of the solidification, we got a lot of cracks. There's a network of cracks that makes the alloy unusable for any practical application. Okay, what can we do? Of course, here we also have some information about the solidification curve, which was calculated based on its own composition by thermocalc, by assuming Scheil-Gulliver solidification conditions. So no diffusion in the solid phases and ideal diffusion in the liquid with equilibrium at the interface, right? And we got this kind of curve, which shows a sharp, let's say, drop in the temperature in the last stage of solidification. Okay. If we add copper, more copper in the alloy, the curve is modified and the amount of cracks is reduced. And if we add even more copper in the composition, we drastically modify the solidification behavior and we can remove all the cracks. Also, there is another issue that can be considered. On the right-hand side, we have the EBSD images of some grains. On the top, we have the structure corresponding to the standard alloy with crack, coarse grain, while on the bottom, we have the 12% copper, which shows no cracks anymore, of course. But also there is a slight refining effect, which might be due to the different temperature of solidus and liquidus especially. Second strategy, let's say. Second strategy goes or concerns the shift in the grain morphology from columnar grain towards at least equiax grain. So again, this is a very standard, let's say, chart showing in a qualitative way the trend for the generation of different structures depending on the solidification condition. On y-axis, we have the temperature gradient. On x-axis, we have the growth rate of the solid front. And the red region here corresponds to the usual condition for laser beam additive manufacturing. We have quite large temperature gradient and quite large growth rates, so that we produce structure which is very refined, because both parameters are very high in value, but also we tend to get columnar grains. Okay, there are studies in the literature trying to modify parameters in order to move out from here, but my opinion is that it becomes very difficult to change so much parameters or so much the conditions still using a laser. A laser intrinsically produces very fast solidification rate and uses very high growth rate. But it's very difficult to modify parameters. The only thing we can do in order to move right here, okay, this could be the region for getting equiax grain. The only way for moving toward this region here is to act externally by introducing some nucleants, some external particles that could promote heterogeneous nucleation in the liquid. Okay, and on the right-hand side we can have a picture of a structure which was generated by using the streak here. It's about 2000 alloy. I can make an enlargement in which nucleons were added in order to promote nucleation. I think it's very nice. Maybe qualitative is not wonderful, but we can understand very easily that the small grain, almost all the small grain, they have a white particle which is associated to it, which is most probably the scandium solid particle, scandium-rich particle that stimulated the nucleation of equiax grains. We can promote the nucleation of equiax grain by creating a dispersion of solid phases that already exist in the liquid, not any kind of phases. Maria Teresa was explaining that we need to have some special properties, but yeah, more in general, we have some standard particles that have been used since lots of years, also in casting and welding metallurgy, to promote nucleation of new grains in the liquid melt. Titanium diboride is a typical issue. It's a typical element or compound that can be used, and you can see the big difference that we can create in the solidification curve by adding TiB2. Okay, so there will be available some solid particles in the liquid melt already from very high temperature. The solidification sequence in the matrix doesn't change, but we can create some nuclei, some substrate in which the grain, the aluminum grain, can grow. Okay, so first we have TiB2, and then a layer of aluminum 3 Ti can create on the formal particles, and then we can induce the growth of the aluminum matrix. There are so many concepts. Unfortunately, there is no time to discuss too much about that. But here I put only three, let's say, of the main issues that we can face or we should consider when designing alloys and when when trying to select the proper inoculant for a specific alloy. First of all, we can think that in order to promote the columnar to equiax transition, we need to work on, I was telling you, at least three main points. We need to have a number of solute atoms in the alloy that during solidification promote enough constitutional supercuting. In literature, we talk about the Q value, which needs to be high enough. Q stands for the growth restriction factor. So it depends on the partition between solid and liquid of a specific element, and we need to have enough segregation in the first layer of the liquid of the solute atoms. So we need to respect this condition. Moreover, in laser-based additive manufacturing, thermal undercooling is also very important, and it is said it is very high, and it can also support very much the nucleation, the heterogeneous nucleation, or let's say the growth of the solid matrix from a nuclei. And then, of course, goes without saying that we need to consider the inoculants, a specific type of inoculants, having a specific crystal spacing matching that of the aluminum matrix. Again, I'm trying to see on a more, let's say, macroscopic perspective the issues that Maria Teresa was talking about before my talk. Yeah? And so we shall consider, of course, the chemistry, the crystal structure, so the type, and but also the size of the particles themselves, and the density, the volume fraction of these inoculants. Then, from a practical point of view, how can we induce such kind of nucleating effect? Oh, sorry. Before doing that, what kind of inoculants can be used? Again, we do not need to invent, or let's say, it's not strictly necessary to invent anything new. From casting science, we know that titanium boron diboride is very common, is very popular. Usually it's not exactly, they do not use exactly the stoichiometric composition, TiB2. They use excess of titanium in the composition of the alloys, so that first we are able to form TiB2, but then additional titanium is used for generating the 3-aluminized titanium, and then even more titanium remains in solid solution to promote constitutional undercooling. But also zirconium is used, also scandium is used, and many other exotic elements can be used. Again, they generate 3 aluminides of zirconium or scandium that act as inoculants for the solid phase of the aluminum. How can we put those inoculants into the powder? Because we cannot forget that we are not talking about casting anymore. Here we need to talk about additive manufacturing, and in general, I will be referring to laser powder bed fusion processes. So what can we do is to pre-alloy the powders, the alloy, to produce the powder. So we start from a melt that already contains aluminum, the alloy elements for the aluminum alloy, and for instance, the titanium and boron. And then we produce the powder, which is a pre-alloyed powder, and then we use the powder that already contain intrinsically the inoculants. Or we can use some elements that will combine during solidification or after the process of atomizing the powder to produce the inoculants. We can simply mix the aluminum powder of the starting alloy with the powder of the inoculants. There has been some works in the literature. I also will show you some information about that, some results coming from this strategy. We can pre-treat the powder particle surfaces to cover them with some nanoparticle of the inoculants. This is a very common strategy, and there are some paper in literature. It's very elegant. It's really wonderful in terms of scientific approach. It produces, in principle, a very good result because we are pretty much sure that the inoculants will be very homogeneously distributed in the melt and in the final alloy, but it's very difficult to industrialize this method here. Or even we can promote in situ reaction between some ingredients to form the inoculants to have a chemical reaction in order to form the inoculants through the melting, or there are some other methods. Here in the next slide, we'll try to show you some results about some of these strategies. Here, for instance, we have some example about using a 6192 aluminum magnesium silicon alloy that was modified by adding zirconium. By adding zirconium in the pre-alloyed powder, in the powder, so melting a liquid alloy that already contains 1% or 2% zirconium and producing a powder out of it, or adding, as Maria Teresa was showing an example, again adding zirconium dihydride powder to the powder of the 6192 alloy, and promote the in situ decomposition during the melting, so that we have zirconium available for the nucleation of the grain of the matrix, and hydrogen that's okay. There is an issue about porosity, but hydrogen in principle should escape from the melt. Again, the usual example by using thermocalc to simulate the solidification goes quite obviously that by adding zirconium 1% rather than 2%, we can increase progressively the amount of solid particles available for the nucleation, while again it is confirmed that nothing happens to the, no changes occur to the solidification curve of the FCC alpha matrix of the aluminum. Okay, same trend. And this is the result we can achieve after laser powder bed fusion of these alloy. The standard non-modified alloy produces quite coarse grain, some cracks, as already anticipated, while by adding zirconium 1% rather than 2%, we can promote shift from columnar to equiax grain. We can understand that the shift is not completed yet. Okay, still there are some regions where the grains are not exactly equiax, but at least we can remove the crack. We can avoid the hot cracking phenomenon. I think here it's a question about having a good mixing, a good even distribution of zirconium in the volume of the liquid and then in the volume of the solid phase. But okay, in principle it works quite well. This is the same alloy with let's say the heterogeneous addition of zirconium dihydride particles that were added to the original powder. Again, they melt and they produce a quite similar microstructure. One additional point we can mention is that also there is an effect on the texture. Actually, the texture of the original alloy was not that sharp, but at least we can claim that by comparing the standard alloy with the zirconium modified alloy, there is a smoothing down of the texture. We can get a more homogeneous crystal orientation distribution, at least. One more strategy I was mentioned before consists in promoting so-called in situ reaction of some ingredients that may form some of those nucleants that we were talking about, we were discussing about. For instance, there's a commercial alloy produced by Elementum 3D company that uses titanium and boron carbide as original ingredients that may react in the liquid melt to form TiB2. Okay, they call it, what's the name? Reactive additive manufacturing or reactive alloy. Okay, actually, apart from the commercial name, which is not important for us, the main concept is that they promote an in situ reaction, making available what we need right in the liquid phase. So again, the story is always the same. We promote at very high temperature the generation of TiB2, then excess of titanium binds with carbon, which is an important issue, to form titanium carbide in order to keep carbon apart from the game of solidification. And then aluminum-free titanium forms with excess of titanium. And also they claim that there is a kind of composite effect because the residual particles that remain in the structure, the titanium, the white ones, and then the boron carbide particles, the black ones, that remain in the matrix to generate a kind of composite material. I'm not aware about how much the strengthening will be with that very small percentage of particles, but in any case, we won't deal with that in my talk today. Again, just to understand the process, how it works, this is again a plot summarizing the stability of the phases under equilibrium, in this case, calculated for standard alloy I was talking about in the last slide, containing originally titanium and boron carbide in the composition. Okay, it's equilibrium. It's not a solidification simulation, but I think it's clear enough. It's good enough for us to understand what will be the stability of the different phases during the process of cooling down from very high temperature, exactly under the laser beam, to temperatures. So from the melt, first we have the generation of TiB2. Then, as we mentioned before, we also have the generation of titanium carbide, then aluminum-3 titanium. Then here, the two lines, the yellow and the blue line, I forgot to put labels here, sorry. They correspond to solidification. Actually, the blue line should be the liquid that is going down to zero at the solidus temperature, and the yellow line is the solid alpha phase that is starting growing from this temperature, which is liquidus, and then we'll go very high, up to 90 and something %. Then again, during the solid phase, we're gonna have again some more aluminum-3 titanium, which precipitates also in the solid phase. And in principle, I don't know if it's true under non-equilibrium condition, we should expect also to have some aluminum carbide right here. But I think it is important to understand the solidification sequence, or what happens during in the solids, in the liquid melts, let's say. And okay, here there are some micrographs just to show you what happens for real. Again, here's magnification of a titanium particle and a boron carbide particle, and here we have some EDS map confirming that titanium is being dissolved progressively in the matrix, but not all the particles are completely dissolved. Boron carbide is here. This is carbon. This is boron. Boron carbide is still there. But carbon is, I don't know whether you can see it, but carbon is collecting around or at that particle, promoting the phases we were talking about. Then let us move, I have to speed up a little bit. Let us move to the second part concerning the thermal treatments. I have to tell you, just to make a link between the nucleation and thermal treatments or strengthening dispersals, that some of the inoculants we could use before, they also play a good role in promoting strengthening by dispersion strengthening mechanisms. Scandium is the most famous, most popular element in this perspective. It helps nucleating new grains, but also it helps in promoting dispersion of small nano-sized particles that induce a given strengthening in the alloy by aging at 300 very high temperature. Here there is an information about, on the right side, there is information about the hardness curve that can be achieved during the aging of laser powder bed fusion processed alloy. The scalum alloy, for instance, is a typical alloy that uses this kind of strategy. And here is a comparison between the curve of the tensile, the stress strain curve of the material processed by LPBF in as-built conditions, so no heat treatment, and aged, showing a significant strengthening effect. So I would like to spend my last minutes talking about how to optimize the thermal treatments. Here I put a number of questions, not solutions, but not answers, but questions about things we have to consider during when designing the thermal treatments. One point, do we really need to perform solution annealing on the laser particle fusion process alloy? Since we should consider that the alloy cools down very quickly and then achieves room temperature by a very short cooling rate in general. Indeed, we can consider these two micrographs right here. On the left side, we have an aluminum 7% silicon alloy in as-built condition. Already have the chance to talk about the very fine microstructure, very nice. While on the right side, we have the same alloy after solution annealing. So holding the alloy at 540 degrees C for a couple of hours. The grain, they coarsen very much. Please consider that the labels here are different. Okay, they coarsen very much. We have larger precipitates. So it's really a pity for in my opinion, to spoil, to remove this very nice fine microstructure. Then, is supersaturation achieved during fast cooling from processing enough for promoting dispersion strengthening mechanism during the following aging? So can we skip, in other terms, the solution annealing treatment? I will show you something about that. What is the effect of multipass and multi-layer laser track on already deposited material? We should consider that the deposited material during the additive manufacturing process is not filling just one thermal cycle, but it will be filling many thermal cycles corresponding to the different laser tracks. For instance, the reference point here in the schematic here will fill its own melting track, let's say, cycle, will cool down, but then there will be another laser track very close to its own position, inducing a lower but still significant heating cycle, and then again and again, and then this will be repeated for the following layers. So I shall add some more powder, and then melt it again and again, so that there is a very complex combination of cycles. The big question is, what is the result of those cycles on the microstructure and on the precipitate condition? And then again, don't forget about residual stresses. Just to give you a few answers, and then we can stop maybe. Okay, these are again three differential scanning calorimetry curve of silicon alloy, which was treated according to different conditions. The black line is standard solution annealing condition, and then when you put the solution annealed alloy in the calorimeter, then we're going to have the two typical peaks for the aging corresponding to the theta double prime and theta prime precipitates that are showing up at a given temperature. When you do the same experiment with an as-built sample, so no solution in treatment, but cooling after processing, we have exactly the same behavior, meaning that the supersaturation is still there. We can have the same aging performance. And the black line, the blue line is for a sample which was produced by keeping the powder at high temperature, so the so-called hot plate building strategy. So in some cases, people that print parts, they preheat the platform and they keep the powder hot during processing to remove residual stresses. And the result of that, usually the temperature in this case, the temperature was 160 degrees, which is exactly the aging temperature. And the corresponding DSC curve of the part produced by this process is a very flat blue curve. So no chance of having any kind of aging. we lose the ability of having aging. But again, here on the right-hand side, we have the same, let's say, information, if you want. The alloy produced by the cold plate, so no preheating, is able to provide quite significant aging, quite significant increase in hardness during aging, while the hot plate sample, they do not show any aging. Indeed, they show stress relaxation and nothing else. Very last slide, and then we can skip to conclusion. For the same samples, then here we have a collection of the tensile behavior, just to add some more information about the mechanical performance, depending on the thermal treatment we can promote on the alloy. So the dashed lines, apart from the vertical and horizontal orientation of the specimen, the dashed lines, they correspond to the standard T6 solution annealing, standard solution annealing, quenching, and then aging. Okay, we have quite low strength but high ductility. However, the bunch of curves here in the middle, the blue and the black one, they correspond to the sample that had been printed with the hot stage, with the hot platform. So they are already aged in the machine. They show an increase in the strength over the standard T6 treated alloy. And that's not bad. It's a good idea, because in principle you can save the post manufacturing heat treatment. But you can understand that we cannot control this process. Depending on the printing time, you can have underaged, peak aged, or overaged material, depending on how much the powder and the material is kept at high temperature. So it's not repeatable, I would say. And then the last bunch of red and purple curves, they correspond to the material that was cold printed and then aged artificially. They show the best performance. And I think that it could be an option for that. But again, there's an issue about the residual stresses. Unfortunately, I have to skip residual stresses because I think I run out of time. We can discuss maybe in the question time. And here there are some conclusions, just some key sentences to summarize what we discussed about. I also would like to mention one of the projects on which we were engaged for the developing of new aluminum alloys. It was funded by EIT Raw Material, name is Simar, Sustainable Aluminum Additive Manufacturing for High Performance Application. This ends my presentation. Thank you for attention.
Thanks a lot, Maurizio, for this very interesting talk. Perhaps we can just take one or two short questions if there are some questions. Yes, Aude.
Yes, sorry, I was very close to get out of the available time.
Thank you for this talk and interesting results that indeed confirm the interest of the grain inoculant solution. I was wondering about the strength of this 12% copper sample. I don't think you showed any tensile curves. Are they interesting? It's like a high content in copper, but maybe that could be.
Yeah, this one here. It's a good question. We do have some data. I cannot show. I don't have the slide to show you. No, actually, it was, of course, it was a very important question you put on the table. Of course, here we were considering only the possible strategy to remove hot cracking phenomenon. And then it goes with it that at the same time, you should also preserve and keep the available strength, or in general, available the target properties to be achieved that should be considered. So here, we were not considering for the moment the mechanical strength, okay, or the evolution of the mechanical strength. I can presume that it might be lower than the original one, okay, which was the silicon-free alloy, but again, it's a kind of compromise or trade-off we have to consider for the right design. Also, if I may, to grab the last 30 seconds, there is one, I think, fundamental how can I say, comment we can make on that. Why shall we modify an already existing alloy? I mean, we are in a kind of temporary situation, or in a kind of environment where we need to create new alloys, and we just grab old alloy, well-established alloy, trying to modify that. But if you look at the metallurgy of aluminum alloy, I think that I'm convinced actually that there are lots of chance to create to design brand new alloys, not modifying what already exists, but creating brand new material, brand new alloys, grabbing or catching only what is needed. For instance, in the aluminum for copper magnesium alloy, there are lots of ingredients, of elements that are not needed anymore, because the process is very different from the original one for which this alloy was developed originally.
I certainly agree. Thank you.
Okay, so as time is flying, what I propose is that if there are more questions, you can also put in the chat, and we will have the half an hour time at the end of this day, and we can complete the questions with that. I think it could be a good solution for that.